Good evening. I'd like to welcome all of you on behalf of the Cambridge Science Festival and the organizations sponsoring tonight's event, the Association for Computing Machinery and the IEEE Computer Society. My name is Edward Friedman. I'm Vice President of our local chapter, the Greater Boston chapter of the Association for Computing Machinery, otherwise known as GBC ACM. Before we begin tonight's presentation, I'd like to tell you who we are and why we think that this event was an important thing to do. ACM is the world's oldest and largest educational and scientific computing society. It's an international organization dedicated to advancing the arts, sciences, and applications of information technology. It has a worldwide membership and is a leading resource for both computing professionals and students in the various fields of information technology and for understanding the application and impact of that technology on our society. ACM has over 30 special interest groups, known as SIGs, in areas as diverse as computer graphics and animation, human interaction with computers, software engineering, artificial intelligence, computers and the physically handicapped, and computer science education. The local chapters like GBC for professionals interested in these subjects. There are also student chapters at universities, colleges, and even some high schools. Our local Greater Boston chapter sponsors monthly meetings, like this one, on a range of cutting-edge topics like electronic voting, computer and network security, online communities for health concerns, self-organizing robots, and RFID, the little ID tags appearing on all sorts of products and places, even being surgically implanted in some people. You can learn more about ACM by visiting the website, www.acm.org, or our local chapter's website, www.gbcacm.org. Computers have transformed our society. Data compression algorithms have given us the ability to create MP3 recordings of voice and music, even a video of tonight's lecture, which will be available for viewing on the WGBH Forum network. Public key cryptography enables us to safely shop online. CAT scans and MRI would never be possible without powerful computers. We've all seen with amazement the accomplishments of the Mars rover and the Hubble Space Telescope. It's even been written that a computer language called Perl saved the Human Genome Project from failure. Before we crash test cars, we simulate the crash in a computer. New drugs are first designed not in vitro or in vivo, in a petri dish or a lab rat, but in silico, on a computer chip with sophisticated molecular modeling techniques. Computational science has become the third pillar of scientific research, joining theoretical and experimental investigations. Oh, and did I forget to mention the internet? It's so ubiquitous, it's hard to imagine what our lives would be like without it. Yet enrollments in computer science have been falling dramatically in recent years, despite projections at the U.S. Department of Labor Statistics that computing and information technologies will be in great demand for the next decade. To quote a Microsoft press release, "The decline in computer science enrollment threatens virtually every U.S. industry that relies on software innovation to build its future." I would add, these days, that means every U.S. industry. We must encourage young men and women to study mathematics, computer and information sciences, for these have become the enabling tools that will allow us to make progress in all other sciences. Which brings me back to the ACM. High school and college students can join for as little as $19 a year and have access to hundreds of online books and over 2,000 free online courses. For $42 a year, they can have all that and can access online every article the ACM has ever published, over 2 million pages worth. Not a bad gift for that graduating senior you may know. If anyone would like to speak to me about ACM on any of this, I'll be available after the presentation. Before I introduce tonight's speaker, I'd like to thank Peter Major. Where are you, Peter? I'd like to thank Peter Major for his work in arranging Jim Gettys to be here. Peter is the program chair for GBC ACM. He pulls together the topics and great speakers for our monthly meetings, and he is also chairman of the local Boston IEEE Computer Society. I'd like to acknowledge our co-sponsor, the Computer Society of the IEEE, the Institute of Electrical and Electronics Engineers. It is in many ways similar to the ACM, but particularly emphasizes the engineering aspects. And finally, thanks to MIT for providing this fine venue. Jim Gettys has a long and accomplished career doing innovative things with computers. He is the co-creator of the X Window system, a distributed client-server windowing technology that is used on nearly every Unix system in the world, and many other systems as well, even Microsoft systems. He is editor of the specification for HTTP, the Hypertext Transfer Protocol, which connects the World Wide Web. He helped found the handhelds.org project to put open source software on PDAs and other handheld computing devices. And he is currently Vice President for Software Development at the One Laptop per Child project. Computers have transformed our society. Tonight, we're going to hear about a project that has the power to transform the lives of tens, perhaps hundreds of millions of children throughout the developing world, and thereby transform the society in which they live and in which we all will live. Please help me welcome Jim Gettys.
We'll do the song and dance with the microphone. How's that? 1, 2, 3. Check, check, check. You okay? Okay. So, I gather I have a pretty geeky audience here tonight. That's fine. That's sort of what I was expecting, given it's MIT. This is a dream that started several years ago, and it's actually been, in some sense, a dream of a number of people in some form or another for a very long time. This particular picture I'm starting off with is a school in Cambodia that Nicholas Negroponte built some years ago, and decided to try to equip all the students with laptops. To his surprise, the laptops were a lot more expensive than the school. Sort of a problem, isn't it? So, in any case, why am I losing here? I've lost some of the bottom of my screen for reasons I don't understand. Let me try one thing quickly. Well, this is frustrating. Yeah, that works. That's readable. So, I want to talk a little bit about why we're doing this, what our mission really is. And then, how do you go about designing a laptop for children? And in particular, children, when I say children, I mean children all over the world. Most children live in radically different circumstances than people in this room. There may be a few people in this room who've been to such places, but probably only a few. I'll then get much more technical about the details of the machine, mechanical design. Something that you normally wouldn't think about much but has dominated a lot of our work is the power system design. A majority of kids go home at night to a home without electricity. Their schools aren't necessarily much better. Therefore, things like power management become really important. And I'll talk some about the software and try to do some sort of a summary. When you start building hardware, it's very interesting. It's quite a different taste to it than building software. In software, you have this infinitely malleable system that you can continue to try to improve. But building a computer is actually much more like sausage making, which is sort of a funny analogy to make, but I think it's correct. You can only make as much sausage as you get all the ingredients for. I mean, all it takes is exactly one component that you can't get enough of, and that determines how many machines you can build. So you worry a whole lot about supplies, multiple sources, and substitution. As much of the recipe as you can, you want to be able to substitute, but there are often some key components for which that's not true. If you make a lot of sausage, you can get some custom ingredients made. Those are useful. The more sausage you're making and the more time you have, the more interesting components you can make. So we're starting off relatively modestly, where we're hoping to make some number of millions of machines in the first generation. That's, by most standards, a lot of sausage, but as you'll see, It's actually not all that much. The devices we all carry around that are really produced in the right sort of volume are cell phones. But cell phones are not very useful for education. So if you know some farmers, you can get some new ingredients made. It's not really a pretty process, and you got to cook it before you really know what it's going to be like. So our mission is fundamentally one of education. We believe that the technology can revolutionize how we educate kids. Okay, this is not a laptop project per se. It's a learning project. Very important to understand that. It influences everything we do. And as you'll see, it influences the hardware design too. Who are we doing this for? Well, kids. Most of them live in the developing world. There are of order 1 or 1.5 billion of them at this point in time. It's an interesting number, isn't it? We're hoping to end up with a machine that lasts of order 5 years, because guess what? 5 years is about how long most kids actually get to go to school, the ones that get to go to school at all. Okay? Do the math. How many per year should we be building? You can do the math. How many people in this audience know how many laptops were built in round numbers last year? I think it's somewhere around 60 million laptops total. How many should we be building per year if this is the basic part of kids' education and lasts 5 years? You can't accuse us of not having certain ambition. Now, the point being, fundamentally, what we want is that people start building the right kind of products. Okay? So we've thought long and hard about this. It's really a very novel machine in many ways, as you'll see. And in the long term, we're delighted if lots of people start building the right machines. Your laptop would be usable for maybe 3 hours in most parts of the world and then be a brick. These are a map of the world. We're hoping to launch in the green countries, followed by probably the red countries. Other colors are. Let's see if this thing works. There we go. This is where we sort of been talking at ministerial level or above, and these are places which, while we've talked to governors of states, we never hear anything from the federal level of government. So far, anyway. This is a little bit out of date. I'm sure it's not quite right. This is our world. This is reality. This is a school in the capital city of Nigeria. Not even a particularly bad school. You see any lights in there? There is electricity at this school in one room. It's available for some small number of hours a day. We've got a problem here, folks. Okay? You think your laptops are going to be very useful for anybody? Do you think you can even get enough power for them? The guy I'm using for display here takes 20 watts on a continuous basis. Sort of a problem. Start multiplying the numbers by hundreds, right? Oops. Another picture of this school. Kids this time. So fundamentally, the point of this project is we're trying to change the status quo, because the current status quo is really not acceptable. Okay? There are much worse places than Abuja. So in some sense, this, however, has been going on for a long time. This is Seymour Papert. The old folks in this audience will recognize that as an Apple II. This is in North Africa. What is it? Probably sometime in the 1970s. Kids all over the world are just as bright, presuming they get proper nutrition. We can only be part of the solution, right? Our part of it is to help the kids learn. There's lots of other problems in this world that, people work on. So this is Nicholas's school again. I want to try again to give a little bit more reality. This is a school in Costa Rica. Those are, I think, HP boxes on the horse going up the trail to this school. That's a computer inside the school. Then you have the problem of how do you get the fuel for that machine. It turns out that the fuel of conventional machines, if you have a generator, becomes a major expense. Okay? So the way we've been building computers fundamentally doesn't work. Just doesn't. We haven't been building the right kind of machines. This is much more recent. So this is in one of our first trial schools in Porto Alegre in Brazil. This is also a major open source free software conference that occurs every year in Porto Alegre, a conference called FISLE. 5,000 people or more registered for that conference this year. Note the reality, kids are out of doors here. You'll see that this is important. The kids are really loving this. It's just wonderful to see. So our premise is kids fundamentally lack opportunity. They don't lack ability. So this is a fundamental tool that we believe at scale can change the equation. A few machines don't really help. Computer labs have been tried for eons and they do not work. No surprise, do the math. You've got a computer lab. Say it's got 10 computers. You've got 200 kids. How many minutes a week do they get? How many minutes a week are they even in school, right? Just doesn't make it. What's more, the whole learning model is very questionable. One of our premises is that kids are creative. Certainly those of you who have kids know that they are creative, if only we let them and don't bore them to death. So our point of view is not that of just passive consumers like an iPod, but much more like things like this nice program here, which can be used to play music, to perform music, to generate music, to synthesize music in a synthesis laboratory, to build your own instruments in the C-Sound programming system. Okay? Let's stop this. So kids also learn by debugging. This is from a demo that we did actually almost a year ago at a conference in Las Vegas, of all places. There's a 50-cent photo sensor here and a wooden spoon and some wire and a connector. The connector goes directly into our audio port because our audio port isn't just an audio port. It can be used as an A to D converter. Okay? It can be. This is the Seymour Papert Memorial feature. He insisted that this be done. Okay? And he was right. It means you can directly take really cheap sensors and start using it in a classroom where the cost is not a USB dongle, but you plug it directly into the machine and go. So Miller Puckett recreated a demo he did like 20 years ago at the Media Lab for conducting music with a spoon. Okay? And a 50-cent sensor. I don't know what it would be in quantity, presumably a lot less than that. So the other thing to think about is fundamentally learning is a collaborative process in large part. You collaborate with your teachers, with your peers, with your friends. If you watch kids, you see them teach each other things all the time. I certainly watch it with my kids. So you have to think about the machine as a social machine, and that building on each other's knowledge is really fundamental. And this is reflected in tremendous amounts of our design thought. And in fact, at a fundamental level, even to the networking and software design. Okay, so if we're going to start connecting everybody, I want my kids to be actually excited about learning foreign languages. They're not going to do it if it's this dry academic subject. In fact, the thing in Porto Alegre that the kids we saw 2 weeks ago were most fascinated by were these strange people who spoke this other language that they'd been studying as a dry academic subject, and so they were insisting we talk English. Not that I can speak Portuguese, you understand. Ich kann etwas Deutsch sprechen, aber but no Portuguese. So, how do we get the kids connected? How do we get the teachers connected? Another thing you want to think about is many of the schools in the world are still essentially one-room schoolhouses in the middle of nowhere. Okay? Think about being a teacher. Teachers in our society are at least valued. We may not pay them properly, but there's a significant amount of respect for teachers, I think, in our culture. That's not true everywhere. And think about what kind of people you get if they've got some number of kids in the middle of nowhere and no support system whatsoever. Okay? So also think about we're connecting the teachers as well as the kids. So, with child-to-child learning, and when I say child-to-child, I mean the kids' friends, but also kids from anywhere else in the world, okay, is really fundamental. So our point of view is wires cost too much. Wireless, particularly when it's unlicensed 802.11 kind of stuff, is really cheap. And people can now build it yourself. And also, it turns out that bandwidth is a perishable commodity. So if you actually go start talking to the telecom carriers, they're often willing to cut you very interesting deals for education if it's not the stuff they can sell. Okay? I didn't mean to show this slide. So this actually is, I think, across the border in Kashmir that they're going. This is a tower that somebody put up in the city of Athens on their own just to start putting together a citywide network, that sort of thing. There's MIT RoofNet that we sit underneath this instant. People are building these ad hoc networks. They're very, very cheap to do. Backhaul is still an issue, but we can share a lot of, make a lot of things a lot cheaper than the traditional way that telecom carriers have done. Okay, so one of the first steps is what do we do about the so-called infamous last mile or last kilometer problem? One of the major features of this machine is mesh networking. This is the first implementation of what is expected to become a standard called 802.11s. It is now functioning on the machine. It actually works. We demo it in public. We use it ourselves. This is only the last month or two that we've really had it running, but it really exists. So you don't actually need access points in the traditional sense. You need somebody somewhere in the mesh who's connected back to the internet if you want internet access. But in fact, the machines forward packets on behalf of each other. So this guy here is happily sending packets, to expand the mesh. Okay. Now, when you start throwing in the interesting point-to-point links like that previous tower you saw, start thinking about meshes of meshes. Okay? Because you can set up a point-to-point link here these days for, I don't know, a few $100 maybe, if that. Actually, much cheaper than that these days. I think we're down at I think Michaelis was talking about a little 2-watt solar cell device with an antenna being somewhere in the $15 range. So how much a directional antenna costs on top of that, I don't know. That'll depend a lot upon what kind of antenna you're trying to do. We'll take whatever we can get for backhaul, obviously. Any connectivity is infinitely better than zero. So there's lots of different technologies, cellular packet data, satellite, all that sort of stuff. Some places have fiber and to random locations. Wherever we can get it, however we can get it, we'll take it. Okay, so now I'm going to really talk more about how you go from just a conceptual model like these down to our reality here. Here being reality. So a kid's laptop had better be safe. Kids do strange things with them. Better be pretty strong. They better be something they can carry. A lot of kids get to walk to and from school, so thinking about your 6 or 7 pound laptop like the one my daughter has doesn't work if you're walking to and from school. Kids like shiny objects, bright objects. Then we come to the harder, interesting technical challenges. Low power, because they don't have a place to plug in typically. Okay. Guess what? Absolutely must be usable out of doors. Fundamentally has to be. Lots of schools, like the one in Abuja there, half the classes are under the tree outside. Okay? That's reality. It better be a creative machine that encourages them to express themselves. And of course, if we actually want to change the world, they better not cost a huge fortune. We better make them economically. So I'll try to address these issues. There are a number of other challenges beside the machine itself, some of which I've alluded to. Things like the power itself, connectivity. This one is particularly entertaining with political uncertainty. Ironically, well, I'll stay out of that on this. The physical environment is a serious issue. The kids not having school buses get rained on. They go through sandstorms, dust storms, that sort of thing. So we worry about that. How do we get them there? That brings up interesting issues like security. How do you make sure they can't easily get stolen in quantities of thousands, right? And poor John there is really tired tonight. So a lot of our software has really gotten big and bloated, and the problem with that is that drives up the cost, drives up the power, all that sort of stuff. So we care about that a lot, and again, cost as always. So if you start looking at where the prices go, I'm not going to really go into this much, but the reality is that if you don't worry about sales and marketing, if it's done the traditional way, you've just lost the battle right there. So you really need to be doing it by fundamentally different ways. We're talking pretty directly to government or directly to governments to buy these in very large quantities, and that sort of thing. Another major piece of this is the display. Conventional LCDs are of this size would be $100 or more. So you just have lost the battle right there. So this display is one of the true innovations here, as I'll get to more. Obviously, the less power, the better. My laptop I have measured at, I think, around 20.5 watts right now. That's not atypical. I think the Intel classmate is probably very similar because it needs a similar size power brick. Actually, identical size power brick as my big laptop does. So what we're really aiming at is a 2-watt machine. Okay. Of course, when you're doing more active things, sometimes you're using more watts than that. It turns out that if a machine's taking, I don't know, anywhere from 2 to 5 watts, it's not good enough. A small child, well, we got into this over a year ago, if they have to physically generate the power they need for the machine, a small child is probably able to do something of order 5 watts. Okay? And, a big burly teenager might get you up to, 15 or something, maybe 20 for some periods of time. You can do a little bit better if you've got a bicycle. Bicycle generators are more efficient, that sort of thing. Our goal's always been how to get to 10x the effort. In other words, get to use a machine for at least of order 10 times as long as you're actually having to do generation. Then there's another challenge. If we want the network to actually work, the mesh network's got to be on 24/7, or at least most of the hours of the day and into the night. Okay? Your laptop, after 3 hours, will stop running. And if it were running a mesh protocol, it would stop forwarding packets. Great. So everybody going to do their networking at 2 or 3 hours in the evening, then go to bed? Maybe. So we really want a system in which the networking can be on all the time. Okay? And the reality is, if the kid isn't pretty confident that there'll be power available when they need it, they're going to figure out, kids being smart, how to turn off the radios. Okay? So it really better be a pretty good bang for the buck ratio when it comes to having the network mesh going on. So we notice the following. Right now, what's my machine doing? It's refreshing the screen, and it might be able to forward packets. Okay? Why is my CPU board on? Okay, that's where most of the power, well, at least once you have a really low power display, which we have here, that's where most of the power, the remaining power is. A conventional laptop, by the way, a conventional laptop is probably dissipating 6 to 8 watts just for the backlight on its screen. This display dissipates anywhere from 100 milliwatts to 1 watt. Okay? I'll talk more about the display in a little bit. So we fundamentally change the equation on the display. The next thing you got to go after is the motherboard. So when it's not doing anything, you actually suspend the machine. So necessity was the mother of being invented. So we can turn off the CPU and most of the system, and on this machine the wireless can be left on and the screen can be left on. We've designed a chip which is called a EconShip, which keeps a copy of the bits that were sent to the screen and can autonomously refresh the screen. Okay? And the wireless chip used, made by Marvell actually, has its own ARM processor with enough RAM for running the mesh in. Now we've actually measured this now. Well, I mean, so I have some real data. The wireless itself is consuming something of order 300 or 340 milliwatts, and then if you figure power supply losses, you're about a half a watt range. I have measured this machine with these prototypes in grayscale mode, consuming 1.15 watts with the screen on and forwarding packets. Okay, personally, I've done that. That's still about 1/10 of a watt higher than I expect the production units to be, because we can actually drive the display at half this frame rate, and that will save us about another 100 milliwatts. But I've measured 1.15 watts. And given a 22 watt-hour battery, guess what? I can actually go for a while. I can read a book for a long time, particularly if it's sunny. Even if it's not, and I'm using, say, 1.5 to 2 watts with the backlight running, I can still go quite a long time, mostly reading. Okay? Occasionally having the machine wake up. Of course, that produces some other challenges, like how long does it take your laptop to wake up from suspend? This one, and we've only just started. We haven't really done any serious performance work on it. Now resumes in currently about 160 milliseconds. And the hardware, this hardware is probably good down to about 63, we think. So a good chunk of which is just synchronizing to retrieve the control of the screen. So you have to sort of wait up to 1 frame time. Okay. Okay. So the good, the bad, the ugly. As I said, the Geode processor is not as fast as we might like. Neither is it terrible. So we think it's about 63 milliseconds. So this is at the very hairy edge of human perceptibility. Okay? So we may not actually always turn off the processor between each keystroke, but we're awfully close to that. And anytime you're idle for even a short period of time, we can turn off the processor and save multiple watts. Okay? There's other easy things that are not worth spending time on. Run the flat panel slowly. I already alluded to this. The wireless itself can forward packets by itself. It's basically a layer 2 mesh for those of you who are computer networking geeks. So given this power consumption, we sort of expect it can sustain mesh for a order of 40 hours, which means hopefully there won't be too much incentive for the kids to try to defeat the wireless. So power management we care about a whole lot. As I was saying, we can do it really, really fast. We expect to be well under 100 milliseconds when we start worrying about it. We're already at 160. The system appears to be running the way you normally expect, but because you've got your screen alive, but that sort of thing. So we hope that we'll end up with a target power consumption, at least if you don't leave the backlight in color mode all the way up, to be something of order 2 watts on a steady state basis. So hopefully be able to run all day for a lot of uses. But relative to conventional laptops, the variation between different use cases is way wider than you're used to, because we don't have the steady state waste of many watts for the processor board and many watts for the display, whether you like it or not. Okay, so different ball game. Okay, so we have to get the price down. So this really has a novel display. There are 2 ASICs we designed for this thing I'll go into. Large volume is really key, and we have to get the costs out of the distribution and sales channels, that sort of thing. We are using open source software for lots of reasons, including the pedagogical reasons. We're obviously worrying a lot about making the software work well on the machine. These are some sort of guesses as what our power consumption should be. We should probably go revise these a little bit. For the real car buyer types, this is what's under the hood. It's basically a geode x86 architecture made by AMD, but it's very low power. There's a 1/4 gigabyte of RAM. There's a gigabyte of flash. We're using a compressed flash file system, which for uncompressed data, it gets us typically around a factor of 2. For things like compressed video, it gets you nothing, so your mileage will vary. There's an SD card slot, that sort of thing. There are a couple of other unique things about this machine. You notice the keyboard is a sealed keyboard. Water and dirt will wreck your regular keyboard very quickly. The other thing is that another unique characteristic of the devices is this touchpad. The center of it is a conventional touchpad, but the whole thing can be used with a stylus. Kids need to be able to learn to write, and we would like them to be able to write on something other than the dirt. And we'd like them to be able to sketch and learn their alphabet, and some of which have thousands of characters. It also has, obviously, a microphone and a VGA resolution camera, 640 by 480 camera. It's amazing what cell phone technology has caused to become insanely cheap. And when things are built in those quantities, we can afford a camera. The kids really love the camera, and the camera has lots of educational uses as well, so it's wonderful. Power is a really major thing, as should be sinking into you. The power in the developing world is unreliable and poor quality. This machine should take anything from about 10 volts or maybe a bit less is rated for between about 10 and 24 volts. We obviously have to worry about somebody plugging it in backwards, because you're messing around with a car battery, say, and you get your wires crossed. We have to worry about voltage surges, all that sort of thing. We also care a lot about safety. In today's news, I saw that Sony is having yet more lithium-ion battery problems, or another recall, same old thing. We know about that. We actually can use 2 different battery chemistries, nickel metal hydride, and if we can get enough of it, we actually really like lithium ferrophosphate, which is a new battery chemistry, which has few of the problems of lithium ion. It's safe. It burns at low temperature as opposed to 1,000 degrees, things like that. Doesn't need recycling. Since we're a nonprofit, OLPC is a nonprofit company, conventional laptops, you'll notice every year or so you get to go buy yourself a new battery, or you start suffering very short battery life on it, because they're typically of order of 500 to 1,000 cycles at best. Ours are being set up for 2,000 battery cycles instead, since it is not a profit center for us, since we aren't a profit-making corporation. We have a gang charger. One of the problems you have in a classroom is even if you had electric power to run them off of whatever, you don't want the kids tripping over the cables. Okay, so in fact we expect that, and the country's feedback is very favorable to the idea of a gang charger and buying 2 batteries, and one can be charging while the other one gets used. Okay, we have solar panels. There's a big one and small one. Solar panel prices have come down a whole lot. When all else fails, there's also a crank and this sort of interesting pull cord device being built for human power when the sun don't shine, like in the monsoon season or that sort of thing. Your solar panels aren't so helpful, and there'll likely be other things as well in the way of it. There's also, turns out, in the developing world, it is very common for people to charge car batteries in one village and move them to another. Okay? Common way of actually transporting electric power. So again, that we can take most things you're likely to throw at it is a major feature. Okay, the display, as I said, is novel. It is truly novel. Mary Lou Jepson, who is our CTO, is one of the world's experts at display technology of all sorts, projectors before this. So in monochrome mode, we are 1200, 900 pixel resolution screen. Okay, it is reflective in that mode. So you can take this into direct sunlight and use it. Try that with your laptop. I'll show you a picture in a moment of what that's like. The other mode is a color backlit mode. What's interesting about it is it's something like NTSC. So there's still intensity information in every pixel, even if the color information isn't at the same spatial frequency. So describing what the color resolution is actually a complex function that depends upon the ambient light. At the low end, you could characterize it as 800 by 600. In practice, it goes up from there. So it's this interesting, unique pixel structure. Since most of the cost of an LCD panel is not the LCD, that's what's been attacked here. So this takes about a third the cost, or it can be produced for about the third the cost of an equivalent size conventional panel, because there aren't 3 color filters, and there isn't a fluorescent light bulb with mercury, which is not a good thing to be spreading all over the world, in it, along with a high voltage power supply, which is required to run the fluorescent light bulb. The fluorescent light bulb is also is fragile. This uses LEDs for a backlight. The backlight strip is something like $1 or $2 and replaceable. Only reason why we worry about replacement is that Libya is very hot. And when you start looking at the lifetimes of the LEDs, they might have to be replaced in certain parts of the world once in the lifetime of the machine. The screen itself takes anywhere from about 1/10 of a watt up to about 1 watt when the screen's turned up fully. So what we're doing with the so-called EconShip is this lets us turn off. In a conventional system, you have what's typically called a Tcon chip, a TFT controller chip. We've added a megabyte of memory, okay? And if you pack 6 bits per pixel carefully, it'll just fit into a megabyte at that resolution. So it's one cheap RAM chip and a chip we'd have to have anyway. It does some other things for us. It deals with some anti-aliasing if we want it, that sort of thing. The fact that the motherboard is right behind the display in this machine means that we don't have to use LVDS or other expensive interfaces to talk to the flat panel. We can use basically what's a a dual-edge TTL kind of signal for it that, again, saves money and power both. So there's no PCB in the panel itself, no printed circuit board required. So in your conventional system, you would, if this had been a conventional machine, you would have had the geode and an LCD, and here we've added these two parts to get that. Okay, the other ASIC we built is sort of the slippery slope story. We found out that the geode's NAND flash controller was, to be polite, pretty bad. Well, actually terrible. So bad that we could not ignore it. So this meant that we had to build another chip. We looked at some of the IDE controller chips that might be coerced into doing something like this. The cost of that is be about the same as running your own ASIC, so you might as well build your own ASIC to do it right and have it work fast. Okay? But once you have a chip, well, you know, there are these extra pins you get for almost nothing. And the countries also wanted a way to expand the storage, so they wanted an SD slot if we could figure out how. And Walter Bender really wanted the camera, and he was right. It's really been a big hit by all concerned. So we ended up building an ASIC. I should say, when I say we, it's Mark Foster was the chief architect of this machine. So he designed this with our friends at Marvell. So it's a chip called Café. And it does those three things relatively cheaply. So what do we end up with? We're worrying about this case, real school, really out of doors, okay? We also worry about this case of kids that are doing it there. So this is a Sunlight readable screen, about a third the cost of a conventional LCD. It's way lower power consumption. It lets us turn, the EconShip lets us self-refresh the screen without the CPU board, that sort of thing. So we have more pixels on the screen than 95% of the laptops in the world. So this is the first 200, well, it isn't the first 200, this size is the first 200 DPI screen. I've seen some high-res screens on PDA-sized devices that are 200 or even 240, but this one is a 200 DPI screen, which is really wonderful for reading. Remember, the economics work a lot better if you aren't buying lots of books or don't need to, and the kids can finally get any book they want, potentially, as opposed to the tragically small number of books that a library might have in many parts of the world. Mary Lou Jepson is the person on the right, and Scott Sung of Chi-Mei is on the left. That is a powered up and running ThinkPad there. I don't want to pick on IBM. Anybody's LCD panel would do equally badly. And there's ours. A little bit of difference. And they're smiling for really good reasons. So as I was saying, we have to be able to replace a book. This helps the economics a whole lot. And in eBook mode, it's pretty clear we'll be up at this sort of 15-hour range. As I said, I've measured 1.15 watts. Probably of order 10 hours in color mode, at least that's my hope, when you're just reading. So the industrial design is another interesting challenge. How do you build something that looks like, that ends up being useful? We want the kids to really value this. We want it to last. It's got to be something that the children value. It's got to be something, to be honest, that is distinguishable instantly as a child's machine, so that questions get asked if an adult is carrying one. Why is that? Theft. Okay? That's the reality. So we aren't just building another boring black or white machine. I don't care. I'll pick on everybody in this. It's a robust thing. This is a lot thicker plastic than you would initially expect. Even more so the next build than this one. We really wanted to put rubber bumpers all the way around it. We've ended up couldn't get the right materials the compromise of toughness versus resiliency is really a tough one. But the antennas in the next build are actually a composite rubber, and that will now, in drop tests, we can take one of these guys and drop it onto the antennas from 5 feet and have it survive. We don't know how much above 5 feet. We keep encouraging Quanta, who's the largest. I should have said this earlier. Quanta is the largest manufacturer of laptops in the world. They build over 1/3 of the laptops in the world. They're our partner in building this. They're building these machines. Okay, so this is built by the 10,000-pound gorilla in the laptop market. It's an interesting experience for them and us. They're not used to dealing with crazies who say, okay, great, it works at 5 feet, now try 6. They're used to meeting specs, spec sheet. Just keep ticking off all the specs until you're done. And we keep saying, well, try it yet harder. And what breaks? And will it cost anything to fix it? And that's sort of a trade-off, which is new. So I think they're finding a lot of fun. We're finding a lot of fun. It is really fun to see how you build things in quantities like that. Unfortunately, they consider their and I understand why, their production process pretty proprietary. So pictures are few and far between of their production facility. So we went through a bunch of different physical designs. These are some of them. We did different. This is sort of the early one, which was the machine with the crank. Putting a crank inside the machine turned out to be a lousy idea. The reason why is to get any decent amount of power output, you're going to need to hold the machine down on a table and start cranking. And okay. Just to give you some of our reasoning in all of this. So the crank's outboard. If you need a crank at all, lots of people don't. You're in a sunny part of the world. We hope most of you may have a little $10 or $15 solar panel instead. That sort of thing. So we started at green, we ended up at green. So initially we're like the Model T Ford, any color you want so long as it's green and white. Eventually there'll be some more selections of colors, but it turns out the logistics of different colored plastics are much harder than you think on a production line. And then there's interesting problems around getting the right colors to the right person. Lots of colors you can't do at all because of cultural reasons, whether boys or girls will find particular, and or the general culture will find a particular color acceptable. Green is pretty universally okay. And it's the green machine. It's also ecologically by far the most ecologically nicest machine. So the first generation of prototypes were assembled in November. That's the first one coming down an assembly line. Takes about 1/3 the number of production assembly people that a normal laptop would take. There's as you have seen, you may want to read a book or play games, that sort of thing. So it also has an eBook mode. Some more pictures of the machine. Infinite labels, all this stuff's on our website. This system has been developed in the open in a way that is completely unique. People have gotten to see the process of building real hardware to a degree that normally is only seen inside of a corporation. So our B1 machine, so-called, would normally never escape a lab. Instead, we built 875 of them. We wanted to build over 1,000, but we couldn't get a particular FPGA that was the stand-in for the Cafe ASIC at that point in time. As I said, just like sausage making, if you can't get enough of a component, that's it. That's how many you build. So there are more. Some of the fixes made B2, which is what this is. The next build in a few weeks in B3 will be substantially more robust. We knew all the weak points within a few weeks of the first run, but it takes an amazingly long time to modify injection molded plastic molds, like of order months to modify them. Not weeks, but months. so it's really tough. Okay, so we worry a lot about safety and environment in this. There's no hazardous substances in this machine. You notice that there aren't lots of sharp points or anything like that. We worry a lot about moisture and dirt resistant, that sort of thing. Shock mounts on the LCD. Obviously, if you drop the LCD onto a rock, it's made out of glass and it will in fact break. Don't do that. But for most other things, it will in fact survive. So there's an interesting analysis we're hoping somebody will do. In fact, I think we've found somebody to do it. What is the 5-year environmental cost of a stack of books relative to the environmental cost of manufacturing one of these? It's an interesting question. I don't know how it's going to actually net out of all of this. But the costs here are actually quite high. Making paper is not a gorgeous process at all. It uses lots of water and nasty chemicals, and it costs lots of money and fuel to move the books around, that sort of thing. How many of you have had kids that have grown up with computers? Almost the same, geeky audience. But you all know that before they can read, your conventional user interface doesn't work, does it? That start button doesn't mean anything, and that dialog box about your machine's about to not work right doesn't tell the kid anything. And they say, Mom, Dad, come help. Or they hit the OK button anyway, with God only knows what consequence. Anything up to and including, oh, Mom and Dad get to reinstall from scratch. Okay, there's problems with this, above and beyond the fact that Mom and Dad may not be able to read either, and have never seen a computer in their life. And in Nigeria, in the trial going on there, the first question of when the village parents got together about computers coming to their school was literally, what is the internet? I'm serious about that. That's what one of the first questions was. People started talking about the internet, and they had no clue. Okay, I alluded to this. So our firmware is open. It allows us complete control. So we're not using ACPI, that sort of thing. We're now capable potentially of booting and installing over the network. We don't want to have to depend upon non-existent cables, non-existent USB dongles. We really have to be able to install over the wireless network in the field, that sort of thing. We also don't want to pay any royalties, and we want the kids to learn how computers really work, which the first thing is you set up a pile of registers to configure the machine, particularly on a geode. Okay, so we're providing a bunch of sort of basic applications, you might imagine. I won't go into these in huge detail. I'll go into some of them. The basic software stack is what you find in a Linux GNOME desktop. And there are a couple of reasons. The really big reason why is the library called Pango, which does by far the best localization, internationalization support for languages of just about anything out there, up to and including Thai. Thai is a fun language. You're supposed to do line break at word boundaries, except there's no space character. So, in any case, Python is being used to pull the pieces together. You can embed a conventional application. That's not where it gets interesting. We are pulling to the fore in our user interface the concept of presence, the idea that people and resources are available in the network around you, and you can see this and you can share and collaborate. And that's being pulled forward in our user interface, as opposed to bolted onto application from behind. Okay, so there's this metaphor of what's called a zoom interface. You notice we avoid a lot of text in the basic UI elements. These are actually rollover sort of buttons, so when you roll over them, you get a little text explanation. But the basic interface is all iconic. So at one level, you have what applications are, or what we call activities, are running on the machine at the moment, who you may be collaborating with. Those are icons for the kids that may end up being pictures when you roll over them in the future. This is a clipboard sort of thing. These are buttons for changing views. This is for searching stuff. And these are applications. As you'll see when you come up here afterwards, there's a lot more applications down here now than this was done first. I mean, it was actually designed first. Then another view is you and your friends and what your friends are doing. So this guy's surfing the web right now. These guys are working on paint programs. This guy's writing something, that sort of thing. And this is the view of the much larger network of the mesh. And you can see that there's a bunch of kids participating in a joint activity. Okay, and maybe you want to decide to join that. Maybe you don't. You can invite people, that sort of metaphor. That stuff's just coming together right now in terms of actually being useful. The views of actually seeing who you have in the network and the like now actually work. Unfortunately, I only have 2 machines here, so it's not very interesting. It's much more fun over in One Cambridge Center when we have a lot of machines and you see lots of other people, that sort of thing. So a few more of the design stuff. The other, as I was saying, this is sort of what a paint activity would be. We have a very primitive one here at the moment. More interesting thing is the idea of a journal. Many of you who have children know that a very powerful learning tool is kids keeping things in chronological order, writing them down in a journal. File names don't work well for young kids. They just don't. They won't remember them. They become a real nuisance. They will remember, oh, I was working on that 3 days ago. Let's go back in time and see what, go find that and figure out who we were doing it with, that sort of thing. So for those of you who are coders, from my point of view, competition is good. If you have a big, slow and power-hungry machine, I'm not very interested in it. But we often have many choices for any given tool. My daughter, who has the free choice, and Dad has not tried to prompt her one direction or another, has had the choice of OpenOffice, Microsoft Office, or AbiWord, and by choice she still uses AbiWord at age 12. We are not trying to make developed world office workers here. The concept that's learning and that you're supposed to teach a young child how to use Microsoft Office is really a non-starter. We want them to learn how to read and write, thank you very much, and science and math and that sort of stuff. How the world works. So small is beautiful, simple is beautiful, open-ended is beautiful. It's really too bad when you find a tool that doesn't let you sort of move on to the next level. The music program here is the people involved really get it. So at one level, a 6-year-old can have fun with this program. It's called Tam Tam, and just pound on keys and have different instruments, anywhere from birds to bass drums to who knows what. Pound on the keys and make some music. But also, the intent is very shortly, probably within the next month, is that the kids be able to perform music together. Okay, so you have a bunch of kids. You then immediately have a multi-instrument band. Then there's a composition pane where, well, you can have the computer generate it for you with lots of different parameters of different kinds of rhythms and beats and that sort of thing. But you can also go in and start actually composing your own music at a note-by-note level if you want to. There's a thing in this for allowing you to play with music synthesis. So if the older kid actually wants to understand how to modify sounds, there's a synthesis laboratory available. And if you really want to get underneath the covers, you can program the lowest level of the synthesis system, which is done by Barry Verco. It's a thing called C-Sound, which is used for a lot of movies for music and or special effects. You just don't know it. So we are putting extremely powerful tools in the hands of what are known to be creative people. So open-ended is good. is hard. It's an interesting challenge to do, and collaboration is key. One of the other things this program will shortly do is let you share riffs among your friends, right? So, for the next step now that we have the mesh working and the basic presence stuff working. There's lots of stuff you can do to help. Guess what? Most of your work on open source software will help yourselves too, in reality. We've gotten awfully sloppy, folks. A lot of the software we depend on, including this Windows system, was developed on machines that had 2 megabytes of memory. These machines have 100 times as much memory as that, RAM. And I had 300 megabytes of disk or thereabouts on that machine. This thing's going to have a gigabyte? Okay. We've gotten very sloppy. There's lots of work to do on memory usage. Guess what? If you make things smaller, they run faster. They use less power. Bloatware is bad. There's lots of kernel work to do for people who like to hack on Linux. Please come help. Power management, out-of-memory behavior, all that sort of stuff. There's lots of UI work, in both generic and specific instances. Localization is a huge issue. In fact, it will eventually force open source projects to revisit how localization is even done. Right now, Linux is localized much more widely than Microsoft Windows is. Small teams can do it without any permission, so there's already Welsh and Icelandic ports of Linux that have been done that are pretty complete. And so, depending how you count, there's somewhere between 60 and 100 languages that have decent coverage right now. The only problem is that there's about 350 languages in the world with more than 1 million speakers. Okay? It's a big problem. And people get to learn a lot of languages. I was talking to a very interesting person, Greg Mortensen, who's written a wonderful book I recommend called 3 Cups of Tea. And he's ended up building an organization mostly of native Pakistanis who've now built over 60 schools in northernmost Pakistan, up near where K2 is. He's a former mountain climber. He says that his kids, when they finish school, which is usually around 5th grade, have learned between 4 and 5 languages. I wish we typically learned. I was talking to a gentleman yesterday who was the language coordinator for a major metropolitan area in Massachusetts, and which there are at least kids who speak like 35 different languages in a school district. The only problem, you might think that would be a good opportunity for language learning for everybody's kids, but by law, all he can do is help them learn English, not the people who speak English to learn other languages, even though there are native speakers of the languages in many of those classes. I find this tragic. Obviously, there's lots of educational software that should be done. There's a fair amount already available on Linux. We're happy to host projects. Please work together worldwide to maximize the amount of good stuff for kids. This is about the kids. So, let's get away from bloated software. We just won't use them, and we'll fix the few applications we really care about. Our browser is based on Gecko. Federico Mena-Quintero is doing some very nice work on finding some of these things. So memory consumption is a big deal to us. Who is this? That's us. This is a community effort. Okay? A worldwide community effort. I don't want Tux to look like that, do you? Keep him the way he's supposed to be, folks. Linus Torvalds, who's the person who started Linux, when you actually talk to him about why did he choose a penguin, notes that, well, a lot of people think penguins, these nice, awkward creatures that stumble around on land and so on, but meet them underwater and they're a very different animal indeed. And go like at 20 or 30 miles an hour and really quite remarkable creatures. I want to make a plea for the end-to-end principle, this being a geeky audience. The original architecture of the internet is that every computer should be able to talk to every other computer in the world. Think of servers as performance optimizations and or holding long-lived data and services, and not as necessary for something to work. For example, email is actually architected this way. Okay. Children should be able to sit down underneath a tree with no server available to them and get work done and collaborate together. So, for example, this means we're in the process of building a Jabber-like chat protocol that works on the mesh but does not require a Jabber server. Okay, as an example of that. So, to the extent possible, network services need to work with no infrastructure. Okay. Systems should not require any sort of manual reconfiguration. There lies madness. You're going to ask the 6 or 7-year-old how to do network configuration and SSID passwords and stuff like this. You got to be kidding. This stuff is actually now doable. We've finally gotten the technological pieces together. There are still scaling issues about for larger schools and the like, where while I believe the protocol designs are pretty much done, the implementations need a lot more work to scale these things up. But this actually is within our grasp now. For similar reasons, we're intending to primarily deploy machines on IPv6. There are 2 reasons for this, one of which is pedagogical, for teaching. If we don't have end-to-end connectivity, I can't have the kids collaborate all over the world. Having lots of little NAT islands breaks that, and it makes it way too complicated to build collaborative software. Skype is about the only thing we've seen in recent years which has managed to somehow work its way around enough of this that it usually works. Okay? Not always, but usually. If we're going to have collaborative applications, we got to do it more easily, folks. And if the kids are going to learn from each other, by God, I want the kids everywhere to be able to work with each other. My daughter, at least with email and web-based applications, is already collaborating with other kids and adults all over the world. Okay. The other piece out of the IPv6 argument is a management one. One of the major problems we're going to face over the next year or so as we start to deploy is expertise. And the idea of having somebody with the right networking expertise have to spend 2 days on a horse or bumping up a road, if they can go up the road at all because it may be closed for the winter because of snow, to diagnose something that could be diagnosed remotely, there lies madness. So NAT islands, as we've found, are really the kiss of death for scalability of expertise. So yes, these machines will also speak IPv4, of course, because we want the kids to be able to use any network any connection to the internet they find, and the first thing they'll do, using things like Anycast, is find a tunnel server and start talking IPv6 to the world that they care about. So we really believe in end-to-end, for both the educational reasons and the technical reasons and the management reasons. So here's where we are, sort of a timeline of this project. It really hit the press first when Kofi Annan in Tunis, what was it? That was about a year and a half ago. The next really major point was when Quanta agreed to build it a month or so later. Okay, who's going to build it that has credibility, right? So we had developer boards last summer. We had late summer display prototypes. Since the mid-November, we've had our first B1 prototypes. We've just started some field trials to shake down the software. We're about to build the so-called B3 ones, and there'll be a B4 and a C test as well. Our production date is currently September 20th, and I think that's now a very firm date. So I want to wrap up by saying thank you. Thank you for coming. Without many of the people in this audience's work over the years, this project would not be possible. Thank you. Without your future help, we cannot succeed. So I urge you to act, not just sit back. This is a huge scale undertaking. From here, you can sort of find anything you like. There's all sorts of things to be done in networking, in software, in administration, in IT, in deployment, in learning. You name it, there's stuff to do. So again, thank you all.
Very much, Jim. It's been a great talk.